One correction came from your friend. So in this theorem about independence, I wrote fx1 to xn equals fx1 to fxn. This was wrong because this should be f1 and this should be fn, the individual cumulative distribution functions. It was a typo, so it's more of a correction. Anyway, I was trying to formulate this theorem. So let's say we have some n-dimensional random vector taking values in some set with probability density function g. And let R be from A to B be a one-to-one transformation into some set B. Okay. And let X be R of Z, so the transformed random variable. So then the PDF of X is given by G of R inverse X this absolute value of the determinant of the Jacobi matrix, well, let me just say for X in B. Where Jx is the n by n matrix defined by, so this is the ij entry of this matrix is the partial derivative of the ith component of the inverse transformation with respect to the jth component of the vector x. And the proof is omitted because it has no probability in it. It is just, it is very well known from calculus, multivariate calculus. So we already applied it in this setting, but I just wanted to give it in a more general way in case you guys need it at some point. Anyway, so that was it about independence and all those joint distributions and so on. So as an application topic, we're going to discuss random vectors, Gaussian random vectors now. Okay, an important class of random vectors. So this is the fourth section and the last section of this chapter. So Gaussian random vectors. So let's say we have some probability space, omega fp. So recall that real valued random variable, let's call it y, is said to be Gaussian if its distribution is given as y minus a squared 2b square root of 2 pi b dy for some a in R and b positive, and we write that y is Gaussian with mean a, so this is the mean, and this is the variance of y. So, of course, we have division by b here, which is not well defined when b is 0, but as a trivial extension, just for convention, let's write that y is Gaussian with mean a and variance 0 if y is equal to a with probability 1. In other words, it is deterministic almost surely. So 0 variance means you are always equal to your mean with probability 1, okay? So if we want to cover the case b equals 0 here, this is how we can do it, okay? So let's define Gaussian vectors. So an n-dimensional random vector x is said to be Gaussian if its weighted sums is Gaussian for all weight vectors w1 to wn. So if every linear combination is Gaussian, then we say that the vector is Gaussian. This b, yeah, it is under the square root because it is the variance, not the standard deviation. So it is more like sigma square equals b. And sometimes people say x1 to xn, so the components of x are jointly Gaussian. So the question is how to construct Gaussian vectors. And one simple answer is that if x1 to xn are independent Gaussian random variables, then they are jointly Gaussian. So the vector x is Gaussian. And so I'm not going to prove it, but I'm going to give you an example of two random variables, each of which is Gaussian, but together they don't form a Gaussian vector. Okay? So in the above exercise, independence is important. Okay, here's one example. So let's say you have z, which is Gaussian 0, 1, and v be such that it takes plus or minus 1 with equal probabilities. Okay, so it's not Bernoulli, but it's like Bernoulli. Not 0, 1, but minus 1 and 1 with equal probabilities. And assume z and v are independent. Okay, so assume z, v are independent. So now define another random variable, y, which is the product of the two. So what is this product? Well, V is like flipping a coin. So you flip a coin. If it turns out to be heads, you look at plus Z. If it's tails, you look at minus Z. Okay? Just some sign flip, right? So this is equal to plus Z when V is 1. And this is minus Z when V is minus 1. Well, we're going to look at a few things. So one is that this Y is Gaussian. Y is Gaussian. Why? Why this is the case? Why is this the case? Well, we can look at the Fourier transform of Y, right? So this is Y equals Z times V, okay? And there are two possibilities, V equals 1 or V equals minus 1. When V equals 1, we have IRZ, indicator V equals 1. When this is minus 1, I have minus RZ, IRZ. V equals minus 1. Okay? If you like, we can put square brackets to make things clear for you. Okay? So far, we just use linearity of expectation. And inside the brackets, we use the fact that V is equal to 1 here, V is equal to minus 1 here. So now, how should we proceed? What is the next step in the calculation? What should we use? How can you evaluate expected value of this term times this term? What do we know about Z and V? Independent. So we can multiply. We can multiply. So since Z and V are independent, we can multiply. So what is the expectation of this indicator? What is the expected value of this indicator? Probability that V equals 1, right? So now if you remember the characteristic function of Gaussian random variables, it is IAR minus 1/2 BR squared, right? There was a formula somewhere. So this is the formula for the characteristic function of a Gaussian random variable. So if my mean is 0 and variance is 1, I have negative 1/2 R squared. So negative 1/2 R squared. This is 1/2. Negative 1/2. What is my R here? It is minus R, right? Minus R squared. So this is the same thing, right? Just e to negative 1/2 R squared. And this is for all R. So we conclude Y is Gaussian 0, 1. Because this is the characteristic function of it. So number 2 is that, so this Y is Gaussian, Z is Gaussian. The second claim is that YZ together is not Gaussian. In other words, they are not jointly Gaussian. They don't form a jointly Gaussian vector. What does it mean to be a jointly Gaussian vector or Gaussian vector? So this means every linear combination must be a Gaussian random variable. So if I'd like to prove that something is not Gaussian random vector, I need to find one weight vector for which this linear combination is not Gaussian, right? So which linear combination should we look at? Which linear combination should we look at? So we have z, and z signs may or may not flip. So this is z, and this is with 1/2 probability plus c, with 1/2 probability minus c. So what happens with 1/2 probability? What happens when y equals minus c? What is their sum? When v is minus 1, what is the sum of y and z? 0, right? So if some random variable y plus z has probability, strictly positive probability of being 0, what can you say about this random variable? Can you say, so would it be possible that this is a Gaussian random variable, y plus z? So I have a random variable y plus z. It has strictly positive probability of being 0. Can this be a Gaussian random variable? Why not? So this means the distribution has an atom, so some discrete structure, right, which cannot happen in the continuous case. Okay, let's do it step by step. So let's look at this probability first, which is like 1 times y and 1 times z. So w equals 1, 1. Okay, so what is that? So this can happen in two cases, when v is 1 and when v is minus 1. So when v is 1, z is equal to y. No, y is equal to z. So I have 2z equals 0 and v equals 1. But due to independence, I can even multiply. When v is equal to minus 1, I have y equals minus c. So I have 0 equals 0, right? Which says nothing, but something true. It's not 0 equals minus 1. It's something true. So I have, well, z equals 0 has probability 0, right? Because z is a Gaussian random variable, so the probability that it is 0 is just 0. 0 times 1/2, and this is just 1/2. So this is strictly positive. So y plus z cannot be a continuous random variable. So y plus c is not Gaussian. So the vector yz is not Gaussian. And due to the exercise, we can also say that they are not independent. By the exercise, this also implies yz are not independent. Because if the exercise is right, if they were independent, they would also be jointly Gaussian, which is not the case here, as we showed. What is even more, what is even stranger is that y and z are uncorrelated. In other words, they have covariance 0. Let's check expected value yz minus expected value of y, expected value of z. Well, these are both 0 because they're Gaussian 0, 1s. And y equals z times v. So this is just z squared times v by independence. So expected value of v is 0, right? So this is 0. Expected value of v is 0 because it is plus 1 with probability 1/2, minus 1 with the same probability, so it is 0. So it is a counterexample for many things, right? First of all, remember if two random variables are independent, their covariance is just 0, right? Because, so remember, independence implies uncorrelatedness. Because if you have x and y independent, then covariance xy is just expected value xy minus expected value x times expected value of y. And this is the product by independence. So you get 0. Now we get a counterexample for this, for the converse. So if you have two things that are uncorrelated, they don't have to be independent. These are uncorrelated, but they are not independent. Okay? These things are not independent. They are individually Gaussian, but not jointly Gaussian. So this example has a lot of nice, corner case features where one needs to be careful about. So you have uncorrelated, but not independent random variables, but also marginally Gaussian, but not jointly Gaussian random variables. So let's try to calculate the characteristic function of a Gaussian vector, okay? Characteristic function. Gaussian vector x. So this means when I pick my weight vector and look at this weighted sum, this is Gaussian. What is the mean of it? It is by a homework exercise. This is W transpose mu, where mu is mu1 to mu n, which is the mean vector of this vector, right? Gaussian vector. How about the variance? Well, this is W transpose CW, where C is the covariance matrix, whose ij entry is covariance between xi and xj. One detail here, which I'm going to skip because we will come back to that later. So one should actually check Cij is well defined in R, okay? Because it's the expected value of a product which should be well defined. But let's skip that detail. To prove that, we need some inequality, which we're going to discuss in the very last chapter, Cauchy-Schwarz inequality. But for now, let's just believe that this is the case. Covariances are well defined. Okay. Anyway, so why did I look at mean and variance? Why did I look at mean and variance? Because W transpose X is a Gaussian random variable. So to specify its distribution, all you need is the mean and the variance, right? So W transpose X is Gaussian W transpose mu, W transpose CW, which also means that its characteristic function is given by so IAR, let me call it AW, and let me call it BW, okay? AWR minus 1/2 BWR squared. I'm just using the fact that every linear combination is Gaussian, so its characteristic function has this formula. Okay? So when you take R equals 1, what you get is IW transpose X, AW minus 1/2 BW. So if you want to write it in full, W transpose mu minus 1/2 W transpose CW for every W. What did we obtain? What is this formula? Expected value EIW transpose X is E to power IW transpose mu minus 1/2 W transpose CW, whatever. So what is this? What is this expression? What is expected value of E to power I times W transpose X? What do we call it? Characteristic function of the vector, right? Of the vector X. Because since we have a vector, we need multiple coefficients, right? So we write X is Gaussian with mean vector mu and covariance matrix C. And this just means that its characteristic function is given as this. And so this mu is in Rn, can be anything, and C is a matrix of dimension n cross n. And in the homework, you guys check that C is positive, semi-definite, well, symmetric and positive semi-definite. Symmetric and positive semi-definite, not definite, semi-definite. In other words, this expression is positive. W transpose CW is positive. And symmetric is, of course, very easy to see because covariance of xy equals covariance of yx. That's why this covariance matrix is symmetric. So whenever somebody gives you a random vector with this characteristic function, you can immediately tell that this is a Gaussian vector with mean vector mu and covariance matrix C. Because Fourier transform or characteristic function determines the distribution of a random vector as well. And using this fact, you can prove some nice result. Okay. So where was it? Okay. So there was this exercise which says that if you have independent Gaussians, together they form a jointly Gaussian vector. And if you have Gaussian random variables with some dependence, they might fail to form a Gaussian vector. But if you have a vector which you know to be Gaussian, so if X is a Gaussian vector, then we have something very nice. Two components are independent if and only if their covariance is 0. For all I, j different. since it's more of a practical day-to-day, we calculate nice things and so on, I don't feel like proving anything. So I leave everything as exercises. Okay. Okay. So one consequence of this is that if you have x with Gaussian distribution, a vector with mean 0, so this is in Rn, this is the 0 in Rn, and covariance matrix is the identity matrix, so 1, 1, 1, and zeros everywhere else. So this means what? Means x1 to xn are independent Gaussian 0, 1 random variables. In this case, we say the vector x is a standard Gaussian vector. So this is, we call a Gaussian random variable in the one-dimensional setting. We call it standard if its mean is 0, variance is 1. In the multidimensional setting, we call it standard if its mean is 0 in all components, and the variances are all equal to 1, and also the covariances are 0, and they are independent, so because of this proposition. Let me write it as an example. So we know that if we have independent Gaussians, together they form a Gaussian vector whose components are independent, right? So can we get some non-trivial Gaussian vector starting with independent Gaussians, right? Can we construct general Gaussian vectors with non-zero covariances and et cetera, just starting with independent standard Gaussians? Okay. The answer is yes, and I will start with an example to illustrate this. Okay. So construction by independent standard Gaussians. So let's say we have Z1, Z2, independent Gaussian 0, 1s. And I'd like to define a vector, let's say x1, x2, x3, by multiplying this z1, z2 with a matrix 1, 2, 2, 3, and -3, -1. Let's call it the K matrix, okay? Now what does that give me? Well, z1 plus 2z2, 2z1 plus 3z2, and minus 3z1 minus z2. Okay. First question is x Gaussian? So x is a Gaussian vector. Let's show this, okay? Well, what do we need to show? We need to show that every linear combination is a Gaussian random variable. So let W be W1, W2, W3 in R3. We look at W transpose X, right? So W1, X1, W2, X2, W3, X3. So W1, X1 is Z1 plus 2Z2. W2 is 2Z1 plus 3Z2. And W3 is minus 3Z1 minus Z2. So if I combine the terms with Z1, I have W1 plus 2W2 minus 3W1. And if I collect the terms with Z2, I have 2W1 plus 3W2 minus W3. Now, how can we say that this is Gaussian? How can we say that this is Gaussian? Z1 and Z2 are independent Gaussians. So how can we say that their linear combination is Gaussian? Still Gaussian thanks to this exercise, right? If they're independent, then they form a Gaussian vector, and that means every linear combination is Gaussian. So this is Gaussian by exercise. So the next question is, what is the mean vector? What is the covariance matrix? This is easier. So the mean vector, x1, x2, x3, is just 0, 0, and 0, right? Because they all have mean 0. Now what is the covariance matrix? Well, first of all, what is the variance of x1? What is the variance of x1? What is the variance of z1 plus 2z2? 5, right? Because when you multiply by 2, it actually, you need to square this coefficient to get the variance, because in the definition of variance, you have a square, right? It's the square expectation of a square. So this is 5. And similarly, the others are 4 plus 9, 13, and 9 plus 1, 10. How about the covariances? Let me write something like this. So variance of z1 plus 2z2, z1 plus 2z2 is 1 times variance of z1, 2 squared times variance of z2. This is 5. Since they are independent, there is no covariance term, right? How about the covariance between z1 and z2? Let's say z1 plus covariance z1 plus 2z2 and 2z1 plus 3z2. So this is 2 times covariance z1, z1, 6 times covariance z1, z2, z2, and 3 times covariance z1, z3, z2, and 4 times covariance z2, z1. So this is variance of z1, this is variance of z2, this is covariance. So since they are independent, these are 0. So I get what? Just 8, right? So this is 8, this is 8. And you can calculate the others, minus 5 and minus 5. And also minus 9 and minus 9. So we can say that X is Gaussian with this mean vector and this covariance matrix. This was number 2. Okay. And indeed, the covariance calculation is not that difficult. You can also calculate it by K transpose. So 1, 2, 2, 3, minus 3, minus 1, and 1, 2, 2, 3, minus 3, minus 1. If you multiply these two matrices. For instance, if you multiply this row with this column, you get 5, right? So there is a shortcut. And you can also write it down as, you can easily make this K a 3 by 3 matrix. So 1, 2, 2, 3, minus 3, minus 1. And let's put zeros here, okay? It doesn't affect anything. And let's also define Z as Z1, Z2, Z3. Since it's going to be multiplied by 0, it doesn't change anything. And you can write X as M times Z. And then, so where Z is standard Gaussian. Okay, 3 by 3 standard Gaussian. So then X becomes Gaussian with mean 0 and covariance M transpose. So M transpose is equal to K transpose. So this part was K. And this is equal to C, the covariance matrix. And you can even shift it by some mean vector mu, and that's not going to change the covariance, it's just going to change the mean vector. So let me state a general result to finish this discussion on the construction of Gaussian vectors. So here's the result. x1 to xn is a Gaussian vector if and only if x is equal to mu plus mz for some mu in Rn, symmetric, positive, semi-definite M? No, of course not. I confused myself with the covariance matrix. Okay, n times n, okay. A standard Gaussian vector Z, the n-dimensional one. Yeah, that's it. That's it. In this case, X is a Gaussian vector with mean vector mu and covariance matrix M transpose. If C, let me say this this way. So if C is positive definite, not semi-definite, definite, namely C inverse exists, then the PDF of X is given by e to negative x minus mu transpose C inverse x minus mu with the 1/2 divided by square root of 2 pi determinant of C for x in Rn. Hopefully I did not make any mistakes. No. Okay. So that's the multidimensional Gaussian density formula. But for that, you need C to be positive definite. In general, C can be just positive semi-definite. So this means, for instance, in this example, it is that kind of a case because you have some redundancy here, okay? You don't really need 3 z's. You only need 2 of them, okay? For instance, if you check the determinant of C here, so check that determinant of C is just 0. Just 0. So it doesn't apply. So this theorem doesn't apply for this example. Okay? It is a lower dimensional density. It actually comes from a 2-dimensional standard Gaussian. It is 3-dimensional Gaussian vector, but it comes from just Z1 and Z2. Just Z1 and Z2. So I will not prove it, but this is the general theorem that you can get about Gaussians. So it tells everything, right? Everything about Gaussians. So any Gaussian vector can be constructed using just standard and independent Gaussian random variables. Okay? In the example, we used 2 standard Gaussians and created a 3-dimensional vector. But in some nice cases, you really need 3 of them to get a 3-dimensional one. In that case, the covariance matrix becomes positive definite. And since it is already positive semi-definite, this is just equivalent to saying that C inverse exists, or all the eigenvalues are strictly positive. Okay? Then you can really take the inverse of this matrix, and this is the density formula. So the proof of this formula is by Jacobians. Jacobi matrix. Okay? So just use this definition, right? We know the density of Z. PDF is just e to negative z1 squared over 2, dot, 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 e to negative zn squared over 2, right? And then find PDF of x. So this is your transformation. So find the corresponding Jacobian and prove that the density has this form.